Well, I thought I'd make a short video over a couple of three problems from section 15.6 on evaluating triple integrals, finding mass and CG, that kind of thing. So now I've scanned these notes to Canvas. Look under exam 3 and you'll see 15.6 examples. So I highly recommend you you download those, because this will go a lot quicker if you have the notes with you, because I'm not going to work these out and watch and let you watch me write and all that kind of thing. So it's just a couple of problems. In class, we have to go so fast. I thought I would do these so you can take some time and just look at them. They're a lot of fun. So this is number 11 from 15.6. You want to evaluate this triple integral, and the integrand is z divided by x squared plus z squared dv, where the region E over which we're integrating, now this is going to be a surface, and it is a good one. It is far beyond my ability to draw. But you've got the planes y equal 1, y equals 4, y equals z, y equals 4, and then x equals 0, which is the yz plane, out to x equals z. X equals z is a plane. Well, this is just plain awful. Now, before we work this, I included an attachment. Here is the graph of this, and I searched long and hard to find something that would graph this. What you see here is z equals 4. That's going to be the roof. Now this is y equals 1, and this is y equals 4. Now in the background is x equals z. It's a 45. The tracing would be a 45-degree line in the xz plane. Now the x-axis is pointing at you in this diagram, the y-axis to the right, and of course that means z is up. So this background here is x equals z. And then here you can see the graph of y equals z right here. So if we put all that together, we're integrating over this little box right here. Now what you've got is the roof of a tent. There's a 45-degree line, and from this perspective you can't see it, but there's a 45-degree line. So what it is, it's got a roof like this. The floor is y equals z. The right side is x equals z, and then you have y equals 1 and y equals 4 with a roof of z equals 4. And I'm telling you what, that's beyond my ability to draw. Okay. So after saying all that, we want to do this now. We want to graph this, and I chose to let the order of integration be dx, dz, dy, because I can integrate that with respect to x. Z is a constant. Z is a constant. Okay. So x goes from 0 to z. Z goes from y up to 4. 4 is the ceiling. And then y goes from 1 to 4. So let's look at the innermost integral. The innermost integral is this. Now the z can be factored out. And what's going on here is just the integral of 1 over x squared plus a squared dx from Calc 2. And when you integrate that, lo and behold, you get 1 over z inverse tangent x over z times the z that you factored out, evaluated from 0 to z. Now, if you let x equal z, you get the inverse tangent of 1. And then if you let x equal 0, you get the inverse tangent of 0, which is 0. The inverse tangent of 1 is pi over 4. So this innermost integral results in pi over 4. It gets better. Now step 2. That's really the hard part of the problem. Now we can factor out the pi over 4, and then we have the integral from y to 4 dz. Well, when you integrate dz, you get z. Z evaluated from 4 to y, or from y to 4 rather, gives you pi over 4 times y minus 4 minus y. And then your last integral is pi over 4, the integral from 1 to 4, 4 minus y dy. And that's very simple to evaluate. When you do the arithmetic, you get down to 9 pi over 8. So what made that difficult was bringing back this old memory of the integral of 1 over x squared plus a squared. I sure hope your instructor showed you how to do that. Of course, all of you should have seen the integral of 1 over x squared plus 1. But you can generalize that integral and replace the 1 with an a squared. And when you do, the integral is 1 over a inverse tangent x over a, where a is a constant. Well, in this problem, z is a constant for the first integration. Very, very cool. Okay, let's look at the next little problem from 15.6. Now, you should know right away when I put a heading on a problem that says really cool, you know there's going to be some mischief and pain in this. So here we wish to evaluate this triple integral over some region t. Now the t is going to be a surface, isn't it? Now the integrand is y squared, and the surface is going to be the tetrahedron that has vertices or corners at the origin, at x equals 2, at y equals 2, and z equals 2. Now I want you to pause the video and see if you can sketch that. Okay, now when we sketch that, we get this. So one edge of the tetrahedron is the YZ plane, one edge is the XZ plane, one edge is the YZ plane, and then finally what I've got here in red is I've connected those points, not including the origin. And that gives me the equation of a plane there, doesn't it? Not gives me, but that gives me a plane. Okay, so for the order of integration, I'm going to begin with z. Z is going to go from 0, obviously, which is the xy plane, up to, if you just pick any arbitrary place here where I'm pointing, if you pick any arbitrary place and go up, you're going to hit that plane. So z is going to go from 0, the xy plane, up to the plane there that's in red. That means I need the equation of that plane. Well, I created a vector from A to B. I labeled this endpoint A and this endpoint B and this endpoint C. So I created a vector from A to B. Let's remember how to do that. That's 0 minus 2, 2 minus 0, and 0 minus 0. And then I looked at the vector AC going like that. So that's going to be 0 minus 2, 0 minus 0, and 2 minus 0. So I've got vectors AB and AC. I need, to get the equation of the plane, I need a vector orthogonal to that plane. So let's cross the two vectors we just found. And when you do, you get 4, 4, 4. A vector with components all fours. So all I need is any vector perpendicular to the plane. So I'm going to choose n to be that vector, and n is just going to be 1, 1, 1. So that's going to be a vector normal to the plane. So that's going to give me a 1, times x minus 2, and I'm using this point to find the equation, a 1 times y and a 1 times z. It's really 1 times y minus 0 and a 1 times z minus 0. Now, if you solve that for z, you get 2 minus x minus y. So that is the equation of the plane. I've got to do all this before I can even begin to integrate this. This is such a good problem. All right, now give that a look. Don't go any further in the video until you understand what's been done here. This has to be done. Okay, let's look at the second. So I'm going to set up the integral this way. I'm going to integrate y squared, and I'm going to integrate dz first. And z is going to go from 0 to 2 minus x minus y. That's the equation of the plane I got just a minute ago. That's the ceiling. And then y is going to go from 0 to 2 minus x. Now, where did I get that? Well, if you look at 2, 0, 0 and 0, 2, 0, in other words, if you just look in the xy plane, you get this. Now, this has a slope of down 2 over 2. So it has a slope of minus 1, and it crosses the y-axis at 2. So y is going to go from y equals 0 up into the equation of that line, 2 minus x. And finally, x is going to go from 0 to 2. So that's my setup. So the first thing I want to look at is this integral here. I want to look at this. And we're integrating with respect to z, so y squared is a constant. You just factor out the y squared. And when you integrate dz, you get z. That's going to be z evaluated from 2 minus x minus y to 0. And of course, 0 gives us no contribution. So the result of the first integral is this. Now that's going to be, if you multiply through by y squared, you can factor this in as 2 minus x times y squared minus a y cubed. Now, I'm going to integrate with respect to y. So I want to integrate this from y equals 0 to y equals 2 minus x. Well, that's going to be y cubed over 3. Remember, the 2 minus x is a constant, so that's y cubed over 3. And then the integral of y cubed is y to the 4th over 4, and this is evaluated from 0 to 2 minus x. And something really cool happens here. When you evaluate this, when you let y equal 2 minus x, you get a 2 minus x all to the 4th over 3 minus a 2 minus x to the 4th over 4. You can factor out the 2 minus x to the 4th, and then you're left with 1/3 minus 1/4, which is 1/12. So integrating the second integral gives me a 2 minus x to the power 4 all over 12. And then finally, the last integral will be 1/12, the integral from 0 to 2, 2 minus x quantity to the 4th. I just did substitution, let u equal 2 minus x, du's minus dx, so dx is minus du. I change the limits when x is 0, u is 2, and when x is 2, 2 minus 2 is 0. We swap these, pay the tax of a negative, which makes it plus 1/12. The integral from 0 to 2 of u to the 4th du, so we get a u to the 5th over 5, so 1 over 60. U to the 5th, so that's going to give us a 32 over 60, which reduces to 8 divided by 15. Now, if you like math, it doesn't get much better than that. That is so cool. That, if I had to give you one problem on the final, and the final could only be one problem, that would not be a bad choice. That covers a good deal of what we've done. Okay, well, I think I've got one more. Yeah, this is number 39. Now, 39, is a mass and CG problem. So we want to find the mass and the center of gravity for the solid E, and with the given density function rho. Now E lies above the xy plane and below the paraboloid z equals 1 minus x squared minus y squared. And the density function is 3, so the density is constant. Okay, now what I've got drawn is not the surface. It's 1/8, or actually 1/4 of the surface. It's the surface in the first octant. There's really 3 more parts to it. So for the mass is just the integral evaluated at the density function times dv. Well, that's going to be 3 times the integral of dv. So what I chose to do to find the mass, since the density is constant, is just find the volume for the region in the first octant and then multiply by 4. So I chose to integrate with respect to z. I'll integrate from 0 to 1 minus x squared minus y squared. Cool. And then now if you look down in the xy plane right here, this corresponds, remember you would have a roof over this, you would have the surface up here. So in the xy plane, I'm just integrating over that part. So this is just the equation of a circle. So y will go from y equals 0 up to the circle. So 0 to the square root of 1 minus x squared. X goes from 0 to 1, because that would be x squared plus y squared equals 1. So x goes from 0 to 1, and then it's times 4. Now you can do this with the mass if the density is a constant. If this was some expression with x and y and z for that matter, then you could not do this. You would have to have the limits. For instance, x would have to go from -1 to +1. Y would have to go from minus the square root up to the plus square root. Okay, so the first integral is just, it's going to be 12 times the integral of dz. When we integrate dz, we get z from 0 to this, so we pick up this. Actually, there should be a 12 there. Then we're left with 12 times this integral over the region in the xy plane. So I'm going to switch to polar. It just screams polar coordinates. So this is going to be written as 1 minus x squared plus y squared. So that's 1 minus r squared. And then we pick up an r d theta from switching to polar coordinates. And we're going to have a lot more to say about one way to get this r without going through that geometry that we had to later. So r is going to go from 0 to 1, and theta is going to go from 0 to pi over 2. And then we have times 12. So you just evaluate the integrals, pretty easy, pretty straightforward. And we end up with the mass is 3 pi over 2. So the mass is going to be 3 pi over 2. Now I took advantage of symmetry because the density was constant. But now when you start calculating these moments, you cannot do that. So let's see what happens. Okay, now for the center of gravity. We could use symmetry, but you've got to be very careful, and generally it's very, very difficult. Because you've got to consider symmetry with respect to the geometry, and then symmetry with respect to the density. I've always been a lot better at integrating things than trying to figure out lines of symmetry, because you've got to consider two things, and I've always found that to be a tough one. So we're looking for the CG x bar, comma, y bar, comma, z bar. Now that's going to be the moment with respect to the yz axis divided by the mass. And remember, we have the mass. That was 3 pi over 2. Now the moment with respect to yz is going to be this. It's the density function with a letter, a variable. And it's going to be the variable that's missing. Here you have y and z, and the variable missing is x. The moment with respect to the xz plane is going to be a y in here. And the moment with respect to xy, there's going to be a z in here. Now, I've made a comment in red here. I wrote this in red. Since the density is a constant, 3, then you only need to look at symmetry with the geometry. You don't have to look at symmetry with respect to the constant. Now, since x is going to be between -1 and 1, and y is going to be between -1 and 1, in other words, you've got that in the xy plane, you have a circle. We know that x is the x coordinate for the CG, and the y coordinate for the CG is 0. In other words, in the xy plane, you can't have any more symmetry in the world than a circle. So the x coordinate has to be on that axis, the y coordinate has to be on that axis. But what I just did does not work if that density function is not a constant. You could not say that. You would have to look at this symmetry along with whatever symmetry is present in this. And I've always found it just wasn't worth the effort. So I was always better at integrating this stuff. But what I'm going to do, I'm going to calculate everything anyway. I only need to do 3 integrals because I already know the mass. Okay, and in these notes I put in all the steps, and there's a lot of them. So for the x coordinate for the CG, you need to find the moment with respect to the YZ plane, which ends up being this. I'm going to do exactly what I did last time, except I'm not going to put a 4 out here. Okay, I'm going to use the full limits, all the limits for y and x. If you try to do it the way we did the other way, for the mass, it will not give you the correct answer. Okay. So I'm going to integrate with respect to z. Z won't change, it's the same limit. X is a constant. I have a 3 out here because that's your density. So x is a constant, we factor that out. The integral of dz is z. Z evaluated from 0 to 1 minus x squared minus y squared gives you this. So this is the result of the first integral, the inner integral. Okay, now we've got to integrate with respect to x and y. Now I'm going to switch over to polar. And what I did, r goes from 0 to 1. So r is going to 0 to 1. And theta goes all the way around, 0 to 2 pi. I've got the 3 out front. That's the density. Where I had x, I put r cosine theta. 1 minus x squared plus y squared in parentheses gives you this. And then we pick up an r d theta. Now I'm going to do the inside integral. I'm going to integrate with respect to r first. That means cosine theta is a constant. So I get an r and an r, which is r squared. Multiply through, I get r squared minus r to the 4th. And when you then evaluate that from 0 to 1, you get 2/15 cosine theta. Now when you do the last integral, you have the 3, that's just along for the ride, times 2/15. Now of course that cancels to give you 2/5. But look what we're doing. We're integrating cosine theta from 0 to 2 pi. The integral of cosine is sine. If we evaluate sine from 0 to 2 pi. Well, the sine of 2 pi is 0. The sine of 0 is 0. So the moment with respect to the yz plane is 0. So we have 0 divided by 3 pi over 2, which is 0. Okay, now let's find the y coordinate for the center of gravity. That's going to be the moment with respect to the xz plane divided by the mass. Remember, the mass is 3 pi over 2. So the moment with respect to the xz plane is the triple integral with a y in this. Remember, it's always x, y, z. X, y, z, there's a y missing, so it belongs over here. Same limits of integration. I'm going to do the same thing as for x bar. We can factor the y out. That gives us this. Then we have a 3 out here. Remember, that's our density. And I'm going to switch to polar. Now, I've got 1 minus r squared. I've got an r d theta from the transformation from one coordinate system to another. And where I have y, I'm going to put r sine theta. Now I'm integrating first with respect to r, so the sine theta is a constant. Factor that out. Multiply through by the r squared, just like last time. And just like last time, we get 2/15. No difference. So now we have the 2/15 times the 3. And we're integrating sine theta from 0 to 2 pi. That's a negative 2/5. I just canceled. Negative 2/5 cosine theta from 0 to 2 pi. That gives me the cosine of 2 pi, which is 1. Minus then the cosine of 0, which is 1. And guess what? We get 0 again. So the y value for the center of gravity is going to be 0 divided by 3 pi over 2, or just 0. Okay. So that's very, very similar to the previous page. Okay, well, let's go and let's see what happens next for z. So for the z coordinate for the center of gravity, that's going to be equal to the moment with respect to the xy plane over the mass. And remember, the mass is 3 pi over 2. So the moment with respect to the xy plane, well, you know what's going to happen. There's going to be a z there. So now it's going to be just a touch harder, because now when I integrate this inner integral, I get a 1/2 z squared. So that's going to be 1/2 times 1 minus x squared plus y squared. All of that squared, which gives me this now. Okay, well, again, I'm going to get a polar. So this is going to be 1 minus r squared squared. And then we pick up an r d theta. Now, if we integrate this inside integral, it is just substitution. Let u equal 1 minus r squared. du is minus 2r dr, or r dr is equal to minus 1/2 du. This becomes a negative 1/2 the integral from 1 to 0 u squared du. Well, now why is that 1 and 0? Well, I change the limits. When r is 0, u is 1. And when r is 1, we have 1 minus 1 is 0. So to switch these, I pay a tax of a minus sign. So I've got 1/2 times the integral 0 to 1 of u squared. That's u cubed over 3. And we just pick up a 1/6. Okay. So this integral, this set of double integrals here, is equal to 1/6. Okay, remember that now. This is 1/6. Okay, so what's left? Finally, well, I should say more correctly that this first integral is 1/6. This first integral is 1/6. Okay. So that means we have to do the integral with respect to theta. So we have a 3 over 2 times the 1/6 we just found. And then, of course, when we integrate d theta, we get theta. Theta evaluated from 0 to 2 pi is just 2 pi. So we get 3 over 2 times 1/6 times 2 pi. The 2's cancel. 3 goes into 6 twice, and we get pi over 2. So the z-coordinate is going to be the integral we just calculated, the moment with respect to the xy plane, which is pi over 2. And then we found the mass to be 3 times pi over 2, or 3 pi over 2. The pi over 2's cancel. So we get 1/3. So the CG for that object with that density is located at 0.13. So, okay, at least you have the advantage now of going through these. You can pause the video whenever you want. And these are pretty nice problems. They're a lot of fun. I hope this helps.